Good evening, Europeans. Let us start with the presentation. The subject of my presentation is there substitutional nitrogen in nanodiamonds, solving a puzzle by magnetic resonance. The main objective of this study, and it's not only a study, it's a survey of the previous studies and the reporting of some new findings in this field. And the main objective is that nanodiamonds, fluorescent nanodiamonds, is within the scope of interest today in science and technology. I think that it makes no sense to describe you how it is, how these objects are important for today. And substitutional nitrogen is one of the most important defects in these diamond structures. Why? First of all, because these defects are among fundamental precursors of NV- centers, the most interesting centers, the more optical and optical magnetic defects in diamonds. And without having a certain amount of P1 centers, there are also called by N0 or C centers. You cannot manufacture fluorescent diamonds. And this is very, very important precursor. Why just magnetic resonance? There are a lot of other spectroscopic methods when you can detect different nitrogen defects. But electronic paramagnetic resonance provides unambiguous identification and quantification of P1. Very, very precise, very, very reliable. P1 EPR spectra in all mono and poly-crystalline diamond samples are characterized by a specific signal, which is characterized by hyperfine structure. It means that interaction between unpaired electron and nuclei N14 provides very, very clear signature of P1 centers, which consists of 3 main lines. But what happened, and everyone observed personally or saw the spectra in many, many publications. But what does happen on nanonization when you start reduce size of your nanodiamonds? One can see that contribution of this characteristic signature in EPR spectra decreases, and then the signal disappears. EPR spectra of small nanodiamonds, disregarding of the origin of their manufacturing, it may be crushed microdiamonds or detonation nanodiamonds or nanodiamonds obtained by laser ablation, consists of 2 structureless Lorentzian lines with no signature of hyperfine structure. What does it mean? Does it mean that there are no P1 centers there? There are such ideas, and our early ideas about the detonation nanodiamond, when we didn't see the characteristic structure, we say, okay, maybe possibly there are no P1 centers there. And we started to look the source of various EPR signals in nanodiamonds and diamonds of different sizes more carefully, just trying to understand what happened there. Okay, we have a puzzle. Where they are? What is inside the puzzle box? Let's summarize. Large diamond crystallites, we can see clear P1 signals. Small diamond crystallites, no characteristic P1 signals. Absolute. 2 P1 centers or substitutional nitrogen really disappeared there in small nanodiamonds. Maybe nitrogen migrates. Maybe it changes its charge and we cannot observe it by EPR. Or another idea, maybe P1 centers remain the same, but its spectral signature changes. Something happens that we cannot observe it by EPR in that form that it may be observed in larger crystals. Let's try solving the puzzle step by step. First publication, puzzle pieces, experimental facts. First publication, experimental publication of more or less careful, let's say, because I am one of the authors of this article, I cannot say careful, more or less careful study what does really happen when you change the size of diamond particle, was published in the beginning of 2015. And here you can see changes in spectra. You can see that for large nanodiamond particles, in this case, it's about 100 and 120 micrometers, you see clear P1 hyperfine structure, 1, 2, 3 lines. This is a characteristic P1 spectrum. Then, when you start decrease in this series, decrease the size, the average size of particles, you can see that this characteristic signal goes down and something new appears. Very, very strong lines of complicated shape rises. And for small particles, you practically really cannot see the hyperfine structure, but see only this strong signal, which, as I will show later, consists of two signals, overlapping signals with the same spectral position. Okay, how these samples were manufactured? Very simple. The manufacturer, these are commercial samples. The manufacturer takes larger crystals, then crush them and separate by sizes, by centrifugation. It means that no changes in the initial content of nitrogen. Maybe it's, in principle, it is possible that nitrogen goes out or something happened there, but look at the numbers. You can see that the number of spin half defects increases and increases very seriously. In spite of this, signal disappears. Then you can see that surface defects which appear due to the crushing, their concentration increases very strongly. And the relaxation nuclear C13 spin lattice relaxation time shortens an order of magnitude. Okay, let's summarize this data. Initial P1 content corresponds to 134 ppm. Okay, the manufacturer shows 260, 2 times larger, but it was measured by optical spectroscopy and it's not precise. This is more or less precise number. When you make crashing and separation, content of surface centers increases. It's logical. It's mechanical defects which are located on the surface and within the interface layers. C13 nuclear spin lattice relaxation decreases, shortens. Why? Because of increasing number of paramagnetic defects, which helps to the faster relaxation. Progressive shortening of C13 relaxation in combination with drastic changes of EPR spectra indicates some effects of strengthening of interactions in small nanoparticles. Another work was done, EPR work was done practically on the same set of samples provided by another company, but we are sure that it is practically the same samples. And this work was done at very high frequency. It's 94 gigahertz. For EPR, it's high frequency. And here you also can see at high frequency, you have better resolution of the broad signal appears in the center and P1 signal. They detected 3 types of signals: N0, which is P1, some broad line due to mechanical defects, and some unknown signal. And in practically, they repeated the same results that were obtained earlier, and independently on this group. Let's go further. Another work was done in 2018, and it's very high frequency and X-band, 9.4 gigahertz. Again, they got the same results. They have broad line, which is even with better resolution, shifted aside. They have P1 signal and changes from this pure P1 signal in large particles to practically absent P1 signal if in 50 nanometer particles and 0 P1 signal at 30 nanometer particles. Okay, the same. And the last work was done in 2020 by this group. They studied these particles, using these nanodiamonds for hyperpolarized C13 MRI. And as you can see from the spectra, they found exactly, this was also done at X-band at 9 gigahertz. They got the same picture on decreasing the particle size and practically the same numbers. Interesting. Let me summarize. EPR experiments provide the same set of results, even numbers coincide, independent of observation frequency. It means that we observe the same things, and these things are quite fundamental. In small nanoparticles below 80 nanometers, characteristic hyperfine splitted P1 signal with this G factor cannot be observed, let's say more carefully, by continuous wave EPR, at least because for pulsed EPR, the picture is not so clear. They do observe them, but by very, very, very specific reasons. I can explain it later or after the lecture. If someone will be interested, I can explain. Ionization causes progressive growth of broad signals with G slightly different from this one, and the total content of paramagnetic centers responsible for these signals in small nanoparticles approaches the same in detonation nanodiamonds, where only these broad signals are observed and concentration of paramagnetic defects is very, very high. Okay, we have a logical question. What could be observed in the case of bottom-up experiment? All the previous experiments were top-down. We are talking both larger crystallites and crush them into the smaller particles. Is it possible to make reverse experiment? Start from small nanoparticles and then get larger particles. Indeed, this experiment was done. This experiment was done by this group from St. Petersburg. they use detonation nanodiamonds of 5 nanometer size in a specific condition. It means the sintering at high temperature and pressure of detonation nanodiamond to get larger crystallites. And they succeeded, and look what happened there. They start from detonation nanodiamonds. This is the signal. Then, changing time, temperature conditions, they appear to larger crystallites from 5 nanometers to about 5 microns, from 1 to 5 microns in this case. And again, they see that this broad central line disappears and typical P1 signal appears. It means that something happens inside which synthesize again P1 defects, or in detonation nanodiamonds, P1 defects were from the beginning, but they were not observable. And only in the case when from small particles you go to the larger particles, you can observe this signal. On increasing particle size, P1 signal comes back, and this broad signal disappears. Interesting. Let's go further. The most puzzling, except of the experimental facts, the most puzzling are interpretations. In 2014, this is short summary of signals observed. It's P1 pattern, hyperfine P1 pattern, broad Lorentzian line, and narrow Lorentzian line. This is an attribution, well-isolated P1 centers located in the core of larger particles provide P1 signal. Crushing-induced dangling bonds located in the interface layers. And the third signal, which is also singlet with no hyperfine structure, line, located with the same G factor as dangling bonds. This group attributed to P1 centers confined in the core of small nanoparticle and strongly interacting with dangling bonds. The structural model is interacting core shell centers. Problem. Okay, even this model that time supplied us with some problems. That time we found no detailed description what really happens with initial P1 signal and how it might be transformed to the narrow singlet line due to confinement. This is our explanation of transformation of EPR spectrum. The initial starting P1 centers remain practically unchanged on nanonization and further fractioning. Crushing of larger particles lead to a transformation of the P1 signal into a narrow singlet line. A reason for such a transformation may be some new interactions there, dipole-dipole or exchange interaction between P1 spins and multiple dangling bonds, which become more effective in smaller nanoparticles. Okay, the explanation of other group, of Yavkin and Orlinsky group, which got the same experimental set of data, but slightly different attribute, the same signals, but slightly different attribution. Again, P1 centers in the core, broad line due to the mechanically induced defects in the shell. And this, the third signal, they said that it is due to unknown centers located in the outer shell of mostly non-diamond carbons. Unfortunately, this is again core shell, but with very, very strange explanation of the third signal. Careful analysis of the intensity of this narrow singlet line goes up on diminishing the size. Origin is still obscure. And why N0 signals return back on increasing particle size? These facts doesn't coincide with this model. Their model of disappearance of P1 signal is very simple. Below 70 nanometers, something happens with P1 centers, and it is converted to the neutrally charged nitrogen N0, which is paramagnetically silent and cannot be observed by EPR. Or they said, okay, maybe on crushing, nitrogen flashing outside the diamond lattice region. And because of this is, sorry, too sensitive. Because of energetically, it's perfect. Okay, we have another model. The explanation is very strange because they really interpret the observed lines in a very strange form. They found void-shaped line. They called it this broad line by void-shaped. But in fact, it's just mix of Lorentzian and Gaussian line, which doesn't work in this system. And the attribution of this broad line is to the vacancies, V minus, localized within the shell. Their explanation is core shell. It means that they suppose that the concentration and parameters of P1 centers in the core in the shell doesn't depend on site. They analyzed core shell and found that, okay, it may be okay, and this explanation is good. When you start analyzing core shell model more carefully, you can see that, in fact, core shell provides you very different numbers. For example, for 50 nanometers particle, which doesn't correspond to their spectrum. In fact, according to the core shell model, pure core shell model, in 50 nanometers particles, you have to see quite strong P1 signal. They don't see it. They see maybe 1/10 of this signal. It gives us a hint that is something bad with this explanation. Let's go further by the fourth group. Okay, the explanation is the same core shell, but the attribution is quite strange of these new signals. They attributed the third line to the dislocation and vacancies in the diamond lattice, which appear due to the nanonization. Okay, again, when we start analyzing core shell, we could say that numbers are against this explanation. Let's look at the core shell model more carefully and try to apply this core shell model to the 5 nanometer nanodiamond case. What is given? Densities of P1 centers in the core and crushing induced paramagnetic defects in the shell are independent of nanodiamond particle size. Most probably these densities are of the same order. G factors, line widths, and shapes are independent as well. Okay, this is a main point of this core shell explanation, of all these core shell explanations. Then one can calculate the ratio of integral intensities of the spectral component due to P1 and induced centers by using very simple formula, and then analyze them. Let's apply this formula to 5 nanometers nanodiamonds and dangling bonds located within the layer of 0.8 nanometer thickness, as it was found by spin probe method and published in 2011. We found that there are two groups of spins in the 5 nanometer nanodiamond, which interacts with the paramagnetic probe on the surface of the center, interacts by dipole-dipole interaction, and it allowed us calculate distances. And we found that the dangling bonds are located within 0.8 nanometer thickness. Let's see what is 0.8 thickness in the core shell model. One can see that the core shell model, the intensity ratio for 5 nanometer nanodiamond should be between 0.3 and 1. Very, very high ratio. It should be observable. Well observable. But what happens in experiments? We can compare 5 nanometer diamond spectrum with 100 nanometer nanodiamond spectrum. What one can see? Nothing in the spectrum of the nanodiamonds, not ratio 1, not ratio 0.3, not even ratio 0.03, nothing. This signal is not observed in 5 nanometer nanodiamonds. It means that pure core shell model practically doesn't work here. This is an indisputable fact. There are no characteristic P1 signals in small nanodiamonds. What it can say us about the real presence of P1 centers in these systems? Nothing. One cannot say if P1 there or not. Okay, let's go further. There are two main arguments in favor of existing P1 in nanodiamonds. First of all, bottom-up experiment, as it was demonstrated above, which says that well-detectable P1 signals appear in micron-sized diamonds grown from detonation nanodiamonds where there were no signals. Another very interesting experiment was done recently in 2022. It's experiments with E-beam irradiation of detonation nanodiamonds. And this experiment causes increase of NV- centers content. Okay? P1 and vacancies are precursors of NV centers, NV- centers. When we increase E-beam fluence, we create more vacancies, and it results in larger NV- centers content. In this case, we found that it is up to 1.3 ppm at the highest fluence. You can see the characteristic spectrum of NV- centers. But it may be happen only in the case of noticeable P1 content in initial 5 nanometer diamonds. They are there. Okay. By the way, it's very interesting that in contrast with larger nanodiamonds, in 5 nanometers particles, to create new NV- centers, it doesn't require high temperature annealing. It's an interesting fact. Here you can see how changes content of NV- centers in detonation nanodiamonds in comparison with 100 nanometers nanodiamonds. You increase fluence, you increase number of NV- centers. This is well known. It is published in many articles. Olga published, and her colleagues published a lot of articles on this case. But interesting that for larger diamonds, you have to anneal the sample to get NV- centers. For nanodiamonds, you can compare. You don't need to anneal it. It appears. Maybe it's room temperature annealing. Okay, it is possible for small particles. The conditions of migration of vacancies in small particles are not the same that in larger particles. It means that annealing in small nanoparticles appears even at lower temperatures, below 100 centigrade. 100 centigrade, in fact, may be achieved when you irradiate the sample itself. In any case, it's self-annealing. But interesting that when you produce Monte Carlo annealing simulation done as a function of particle size and P1 content, the highest probability for NV- formation in 5 nanometers detonation nanodiamonds appear at P1 concentration of the order of 900, 1000 ppm. Very, very high concentration. You can see at this Monte Carlo results of Monte Carlo simulation. You see, this is the region. It means that to get this result with NV- centers, you have to have there very high content of P1 centers. There is no other explanation of these results. It means that negatively charged substitutional nitrogen defects definitely exist there in 5 nanometer detonation nanodiamonds. And not only exists, at very, very high concentration. How it can happen? Okay, let's suppose that they really exist. Let's try to understand what happened with the EPR spectrum. And this work was recently done, which describes size dependent of X-band EPR spectrum in diamond particles. We revisited this approach on the basis of the same core shell model, taking into account that when you reduce the size of nanoparticles, there are many interactions between magnetic centers which become stronger, and it dictates the new shape of EPR spectrum. This is careful revised results. You can see that on diminishing size, the hyperfine lines disappear. The satellite lines on both sides of the central line disappears. Broad line, which is quasi-Lorentzian, appears, and total content of spins gradually increases. Here the result of the concentration, and very simple calculations which show that it should be in the case when you have the, and it was justified experimentally, that the surface density of dangling bonds doesn't depend on the size of the particle. It's logical. The initial particles are cubic diamond crystallites with sizes of about 100 nanometer, which contains certain amount of P1 defects of substitutional nitrogen. It depends on the synthesis. When you start crushing these particles, it results in transformation of initial microcrystals into an ensemble of small nanodiamond particles, characterized by a broad size distribution from several nanometers to several micrometers. This is a reality. You cannot separate them by size perfectly. Something, in any case, the distribution exists. Upon crushing of a diamond microparticles into several tens and hundreds of small particles, dangling sigma bonds appear along the cleavage surfaces. And okay, applying this simple formula, you can see that this fit provides real numbers. It is achieved, the best fit is achieved for the density of P1 centers about 140 ppm and density of surface spins 0.3 spin per nanometer square. And the experimental value are the same, 6.7, 10 power 18 spins per gram or 134 ppm. Very good coincidence. Okay, let's analyze how nanonization changes the contribution of different paramagnetic centers into the total content of EPR observed spins. We did very simple thing. We just subtract P1 signal from the signals from the experimental signals for different concentrations. What remains only these lines, and this line was deconvoluted into two Lorentzian signals. One is broad, which is attributed to dangling bonds, and narrow of unknown nature. Let's plot these results. When you change particle size, decrease particle size, you can see that you have increasing number of dangling bonds and increasing contribution of this narrow signal. Indeed, it's practically zero for larger particles. Then it goes up, 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 up. And for smaller particles, it reaches what? Really? Wow. It reaches the initial concentration of P1 centers in large microcrystals. Oh, really? Does narrow Lorentzian line originate from P1 centers? Most probably yes. No? Okay. Next step is trying to explain it theoretically. Not exactly theoretically, semi-phenomenologically. Okay? We carefully analyzed all interactions between paramagnetic defects in the nanoparticle using the core shell model. There is a hyperfine interaction which provides with a certain EPR, hyperfine splitted EPR pattern, dipole-dipole interaction, of course, because there are magnetic centers, but dipole-dipole interaction for all reasonable distances cause line broadening. You cannot get, by using dipole-dipole interaction, you cannot get narrow singlet line. Okay, dipole interaction between P1 centers is constant. It doesn't depend on the particle size. They are inside. No one moves them. Dipole-dipole interactions between surface centers also doesn't change because you have the same density of surface centers. Only exchange interactions may cause collapse of the hyperfine pattern and line broadening. And we will analyze various kinds of exchange interactions here. Very interesting. It was proposed the mechanism of indirect exchange interaction between bulk centers. Bulk centers in this case is P1. Just to get smearing of the hyperfine structure, you need some interaction between these centers when the hyperfine structure originates. It was proposed a model of indirect exchange interaction similar to RKKI interaction, which has some reasons for the surface centers. And when you start to compare different energies of processes involved in the formation of EPR spectrum of bulk centers, you have to analyze the hyperfine energy, direct exchange interaction, which are independent of size and may be excluded from the consideration, indirect exchange between bulk centers, and interaction between surface centers, direct exchange interaction between surface centers. All of them are tightened together, and this is a formula. I don't have time and even wish to enter the theory. You can find it in the article, but this is a formula for indirect interaction. And this is calculation using this formula. We can state that the critical radius of a diamond particle, R critical, exists, and at this radius, the characteristic hyperfine pattern disappears, and it is determined from the condition that the energy of indirect interaction between P1 centers and the energy of hyperfine splitting are equal. Here is the point. It means that it happens at critical radius of about 35 nanometers, or particle size about 70 nanometers from numerical calculation. And it means that for all radiuses below the critical radius, one cannot observe hyperfine structure due to the indirect interaction between P1 centers. At the same time, when you have critical radius of the particle larger than critical radius, you can see hyperfine structure. Okay? Now we have very, very clear rules how to interpret the polycrystalline diamond samples, EPR spectra of polycrystalline diamond samples. And when you see this spectrum, you have to follow these rules and everything will be clear. First of all, each polycrystalline sample is synthesized or manufactured by crashing, or synthesized as a small particle by detonation or something else. Each such a sample is an ensemble of particles of different sizes. Perfect separation by sizes doesn't exist in practice. Real polycrystalline samples may be divided by sizes into three main groups. Group A, large micron and submicron diamond particles with a size above half micrometer or 500 nanometers. Group B, medium nanodiamonds with sizes between 500 nanometers and 70 nanometers. And small nanodiamonds with sizes below 70 nanometers. Considering that main defects in these systems are P1 and dangling bonds, and this is true. Of course, there is a paramagnetic nickel there. There is a lot of other paramagnetic centers there, but their contents are incomparable with these two main players. One can say that for group A, the larger the size distribution, the larger particles prevail. The content of small nanodiamonds for group A is negligible, and EPR spectrum consists of well-resolved hyperfine structure due to P1 centers, superimposed on the wide low-intensity singlet line due to dangling bonds. They are there, but not too much, let's say. But for the group B, when you start crushing your large particles, you have noticeable amount of large particles above 70 nanometers and a certain amount of small particles with sizes below 70 nanometers. In the EPR spectrum, you have decrease of the hyperfine splitted contribution due to weakly interacting P1 centers in larger particles, broad line due to the dangling bonds, it becomes more intense because of the decreasing sizes. And the narrow line, singlet line appear, which also increases when you are going to the smaller sizes. The later narrow line originates from interacting P1 centers in smaller nanodiamonds with diameter of below 70 nanometers. In the third group of small, really small nanodiamonds, the distribution is very different. It centers at smaller sizes, and you have no practically larger particles. The content of larger particles is negligible. The spectrum consists of two overlapping intense singlet lines. One is broad, and it originates from the dangling bonds, and narrow line originates from P1, but interacting P1. No hyperfine splitted satellites are observed in this EPR spectra. This situation was described previously in the literature. And the author of this explanation was Lewis Carroll in Alice's Adventures in Wonderland. On right side the cat, and this time cat vanished quite slowly, beginning from the end of the tail and ending with the green, which remained some time after the rest of it had gone. Well, I've often seen a cat without a green, thought Alyssa, but a green without a cat? It's the most curious thing I ever saw in my life. Lucia said, you don't know much. And that's a fact. On diminishing nanodiamond particle size, EPR signatures of P1 centers behave like Cheshire cat. They disappear, remaining something, a green. Carefully analyzing a green, we proved there is a cat behind. Substitutional nitrogen defects do exist in small nanodiamonds with no changes of their origin. Keep greeting the cat. We know who you are. Thank you very much. And this is a list of my colleagues who contribute to the solving of this puzzle. It's a group from Yofi Physico-Technical Institute, Professor Wool, Dr. Osipov, Professor Zegra, theoretician, and Dr. Samasvat, also theoretician, Dr. Alex Panish from our group, Dr. Takuya Segawa from ETH Zurich, and of course, Olga and Nick. They also help in understanding of what is really happening there. Thank you very much.
Alex, thank you very much for your great talk. It is really very, very thorough, very in-depth analysis of very important topic.
Thank you.
And also say your ability to pose questions, to raise questions, and then gradually, step by step, addressing them, replying them is very great. And also your romantic interpretation of the parallels.
I'm very sorry for jumping slides, because the sensitivity of my mouse is it is too sensitive.
It was not a problem at all.
Slides.
So we are open for questions. Please, you can just unmute yourself and ask your questions, or type them in the chat mode, and I will read a question.
Oh, Alex, yeah, I just want to say this very interesting talk. I thought it was very nice to see those models that you showed converge to the predicted values. Yeah, it's very nice. A nice history of how this question's been answered. I guess my question is, how can we then use this to? Is there a way we can use this to produce better, smaller particles? Because we know from fluorescence, at least, that okay, there are certainly active NV centers in in detonation and as well as in HPHT particles that are, you know, even down to 15 nanometer. So, but the fraction of, say, NV centers, or the fraction of particles containing active NV centers is typically very small. I'm just curious, like, how do you think we can use this information to try and develop, say, better small particles? Yeah.
Okay. First of all, this information happens us to understand what if you will use from the beginning, if you will use small particles, and usually when you have starting nanodiamond material, you start to check what is inside there. You know that in small nanoparticles, for example, in detonation nanoparticles or in nanoparticles are obtained by laser ablation or by DuPont method, there is a certain amount of nitrogen, but no one knows how many P1 centers are there. Substitutional nitrogen. Just substitutional nitrogen helps you in predicting a result of irradiation, for example. How to produce NV centers. And having this knowledge from the beginning, you can analyze the EPR spectrum, and in which you didn't see the P1, but you know that they are there, and you can measure them using the integration of this line as it was done for detonation nanodiamonds. And we found that in reality, in detonation nanodiamonds, you do have 2-3% of nitrogen, but only 900 or 1000 ppm of substitutional nitrogen, which will provide you, after irradiation, with NV centers. The same will be with each small nanoparticle. You synthesize something by HPHT, it doesn't matter. You did small sizes. From the beginning, you have to estimate what is inside. Having known this estimation, it will be hard to predict the efficiency of your irradiation and annealing results. That was the point, and we use it for detonation nanodiamonds. In that work with a Japanese group, we use it, and when they found the results of Monte Carlo simulation, they were not surprised getting this large number, because we estimated it for detonation nanodiamond and found that it should be the same. And in this case, they got perfect result of theoretical calculations with the real measurement.
Yeah, I think it's also interesting because of the very high content of the nitrogen, and well, I guess you didn't comment on their brightness, but their ppm is, you know, I think it's got up to like 1.5 ppm or so.
With brightness, there are real problems which are not solved yet, because you have, in addition to the very high concentration, you can get, you know, that the 1.3 ppm were achieved in 5 nanometer detonation nanodiamonds by, let's say, 1.5 E19, 1019 fluence. But if you increase fluence, it was a linear. If you increase fluence, you can get even higher numbers. But the problem is that in small nanoparticles, as we demonstrated, you have a lot of interactions which may affect fluorescence. And it's really not good. It's really not good, and one have to think what one can do it with this one. You can get high density of NV centers, but bad fluorescence due to the interactions. Very short correlation times. This is a problem. This is a problem. But step by step, we'll try to understand what happened there.
Okay, thank you for answering. Alex, I also have a question. So
Yes.
this phenomena of disappearance of hyperfine structures with nanodiamond size due to induced interaction to all these multiple dangling bonds, it should be also typical for other paramagnetic centers in nanodiamond particles, right?
It's very
What
good
about
question.
NV minus? Do you see something similar what you observe for P1 for NV minus?
Okay, this is a very good question. Interesting that it isn't.
Mm.
It isn't because, in principle, I show you again. I come back to the spectra of irradiated detonation nanodiamonds. Yeah, here it is. No, sorry.
Actually, we can go from presentation mode just to regular mode. Then it will be
Okay, look at the spectra. We can see that when you increase when you increase the fluence, this signal grows, but nothing changes there. The interaction between NV minus centers is not strong enough to change something in the spectrum. Interaction between NV minus centers and dangling bonds really affect the relaxation times and the correlation times, of course, but it cannot smear out the hyperfine structures there or fine structure of NV minus centers. Why? Because there is not enough the centers in comparison with P1 to apply the indirect exchange to NV minus centers. I think that maybe at very high frequencies, high densities, if at high fluences you can achieve higher densities of NV minus centers, you may see something. But when you have 1.3 ppm, it's nothing in comparison with the initial 130 or 900 ppm in DND. There are interactions, but they cannot change the spectrum itself. It's one of the possible explanations. But what's interesting that except of this signal, which is forbidden signal, so-called allowed signals in small nanodiamonds disappear as well. It's still not explained, but I think that the mechanism of disappearing these lines should be also related to exchange interactions between all the centers inside, because you have a very dense salad of different centers, and all of them interact.
Another question, maybe let's take, say, good by your criteria particle, for example, 70 or 80 or 90 nanometers in size HPHT. And if we would surround it with some magnetic noise species, molecular species, say of non-diamond origin, can you observe broadening of hyperfine structure due to multiple artificially induced, I don't know what, some nitroxides or maybe metal like gadolinium.
No, broadening definitely we can.
In P1, right?
we can observe magnetic particles attached to the surface of nanodiamonds, even small or larger sizes, very strongly affect, but they affect the hyperfine structure by broadening. But what's interesting, when you have quite clean diamond and reduced size with no new magnetic impurities there except of dangling bonds, the line, P1 line, doesn't change, it just goes down with no broadening. The broadening is a very, very known mechanism, and it also works even for larger particles. And I think that this magnetic noise will affect brightness and will affect all parameters of NV minus centers. I think that the magnetic modulation method is based on this effect. On you also change the relaxation time. Definitely.
Okay, thank you.
Can I ask the question? It's a Maxim Warner from Kansas State. So it's like a question from chemists. So how your explanation fits into this bottom-up approach, or vice versa, bottom-up approach fits into your explanation? Because my understanding that when you're taking a small nanodiamond and start growing like a larger nanodiamond, so basically you should effectively eliminate on dangling bonds on the surface, which so
I think that if you start with small nanodiamonds with a huge density of P1 centers, huge, we found it, 1000 ppm, let's say, then you apply some hard treatment like sintering at high temperature and high pressure. You cause some quenching of dangling. First of all, you cause quenching of dangling bonds.
Yeah.
And if you reduce dangling bonds, they don't affect the hyperfine structure of P1 centers, and it comes back. Of course, in these hard conditions, there are many processes, migration of nitrogen, maybe recharging of some, and in the final larger crystals, you don't really see 1000 ppm of substitutional nitrogen. But anyway, what do you really see there is the rest from that high amount of P1, which was initially in the DND particle. And
well, how about not that drastic conditions? For example, you can eliminate all those dangling bonds by, for example, reducing them chemically, right? Without changing the nanodiamond size.
Okay,
right?
this is a good question. This is a good question, and I would like to see this experiment with quenching of dangling bonds. In fact, when you quench dangling bonds, you have to recreate hyperfine structure in EPR spectra of this.
That's what I was thinking of, yeah.
Yeah,
and then there is no need to increase the nanoparticle size.
And I am sure that it should be, but the main question, how can you do it? The problem is that the dangling bonds are not a surface paramagnetic centers. The most of them located within the interface layers. How to quench them within the interface layer? This is a problem. If you know how one can solve this problem, I will be glad and will ask you to take a powder of detonation nanodiamonds and try to do it.
So you're saying that they are not accessible to small,
They are
for
not.
example,
They are
already?
not accessible. You can reduce. You can reduce some by temperature treatment, as it is done by Czech group. You can reduce number of. You can reduce not number. You can reduce this layer, but even when you reduce it by temperature, you create new centers, paramagnetic centers there. And the density, unfortunately, doesn't change seriously. It remains about the same. How to take them out, totally take them out, I have no idea. I have no idea. It would be very interesting experiment, but how to do it, I don't know.
I might, if I
I
could
see.
add one more comment just on some recent, I think Peter Mauer's group recently just released the paper on archive. And I've seen the same thing. If you grow like a silica shell around the particles, I've not tried this on, say, detonation, but if you grow a silica shell, you see like a considerable reduction in the intensity of that central line in the EPR spectrum. So that could be something interesting is happening on, well, obviously at the surface, but
Then, which means that those centers were accessible to any,
Well,
chemical interactions. At
there's
least some of them.
Yes, I'm sure there's some on the surface, but not all of them. Yeah.
Unfortunately, I didn't see that article. Silica shell over the detonation nanodiamond particle?
Yeah, I think these are HPHT. I'll send it to you. Yeah, it's interesting.
Could you send it to us too?
Of which size?
I believe these were like 50 nanometer or so. Yeah, but I observed similar behavior also in silica coated. Like you see a suppression in the signal intensity and EPR of that central line, which you can attribute to these surface dangling bonds that are in the subsurface, near subsurface, like you were saying.
It sounds,
yeah,
it sounds very interesting. It sounds very interesting. Okay, it would be interesting to do it with the smaller sizes, and maybe I don't know what is the mechanism of quenching of this dangling bonds, but if it is possible, it would be great.
So how about to use just a classical phantom system to generate OH radicals and just to see what would happen if you treat like nanodiamonds with this OH radical? Will this central line disappear or at least diminish? Because it's pretty small particle, OH radical. If let's say
if it goes inside the interface,
I mean,
layer,
if you do,
why not?
if you coat it with a silica, it does mean that silica goes inside the crystal structure, the nanodiamond crystal structure. So obviously there is some chemical bonding to those dangling bonds.
Okay, it's interesting.
Right?
In fact, we know that there are some real surface centers there, and you can quench them. But the general amount of the surface centers is quite low. It may be 1/10 of the total amount of dangling bonds. We did it with the experiments of pumping of the system. In this case, you don't reduce by pumping, but if you reduce oxygen from the surface, new centers appear due to the lack of interaction with paramagnetic oxygen. And it means that they are outside. They interact with oxygen. But okay, again,
I think, sorry, I think the discussion going on. Nicholas, please moderate. I have a doctor appointment, so I will have to leave.
Okay.
But please continue.
Thank you, Olga. Be
Alex,
healthy.
again, thank you so much, and thank you everybody
You're
for
welcome.
attending the lectures. We
Thank
will
you for this
continue them in September.
great opportunity.
In September.
Mhm.
Okay, bye.
Bye. Okay, let's continue. First of all, can you send me this link
Yes,
to this,
I'm
to
gonna
this
send it.
article
I
with
will
silica?
send the link.
I missed it.
Yeah, I will. It's a preprint. I'll just paste it in the chat.
Okay.
Yes, please.
Yeah. There we go. Hopefully that.
Okay.
Yeah, it's rather interesting. I
Maybe
thought.
how did they explain this mechanism?
They are proposing some band bending model at the surface, but yeah, that's kind of my general understanding at the moment. I don't understand it in great detail yet, but I will say that I've also done the silica coating and observed similar results on some, say, 40, 50 nanometer HPHT particles. Yeah, so it's yeah, you see this big reduction in the intensity of this central line. I think it's in figure 2 actually in that paper. You can see this EPR spectra. Yeah, so it's very interesting.
Okay, interesting, and
Yeah,
I would be very thankful if I can get this samples and try to touch them and study them in more details.
Okay, well, yeah, I think we're probably taking up the discussion. If there are any more questions from the audience, we're happy to discuss.
Okay.
Good. Okay, well, I guess everyone is satisfied with questions. So I think, yeah, it's very interesting scientific work here. I think it's very carefully done. I think in general, it's very interesting.
I think it's very interesting, yeah.
Yeah, hopefully this paper that's will be useful to folks as well.
We see a lot of mystery things happening when the size gets into like single tens of nanometers as opposed to bigger ones. There's something happening.
Something happened. Really.
Thank you very much.
You're welcome. If you have questions, please write me. I will try to answer them.
Okay.
Thank you.
All right.
Thank you. It was a good talk. Yeah, thanks.
Yeah.
Thank you.
All right. Well, if no other questions, yeah, thank you. Thank you, everyone.
Okay. Bye.
Bye.
Bye-bye.